Hi everyone, my name is Ching, and today we are going to talk about computer memory hierarchy. And then we're going to spend more time to deep dive into CPU cache design. Before we get started, let me show you something. I've been shopping for a new MacBook recently, and here are some of the configurations I can choose from. For the additional $200, you can get either 8 gigabytes RAM or 256 gigabytes SSD. Confused? We are all greedy sometimes, but what we really want are three things: large size, high speed, and low cost. But it's very hard to achieve all three of them at the same time. Let's forget about computers for a while. Think about how you efficiently organize your books at home. You have a few books on your desk, which you may use every day, such as a computer architecture book. Then you have much more books on your bookshelf, which you may occasionally need, such as all other college textbooks. And you have lots of books in your garage, most likely the books and magazines from your high school. You don't expect to use these anytime soon, but you know you can find them if you need to. In this way, you can easily store a large number of books and at the same time can have fast access to the books you need the most. The concept behind that is called locality. Basically, it means if an item is used by CPU, then two scenarios are most likely to happen next. First, this item will likely to be used again very soon. This is called temporal locality. Second, the nearby items will tend to be used soon. This is called spatial locality. The concept of locality is not just for computers, it is in everyday life. In our books example, if you're reading a book now, say a computer book, then the next moment you'll most likely still be reading it or cross-checking another computer book, which you took all together from the bookshelf a few days ago. Because of locality, computer memories are organized in the same way: a small amount of expensive and fast memory, and large amounts of cheap and slow memory, achieving the highest possible access speed while minimizing the total cost of memory system. This memory system is called the memory hierarchy, and it can be represented as a pyramid. At the top of the pyramid is the registers. Registers are very small memory space. Is a very small memory space inside CPU that can store a small amount of data really fast. The next level below is cache, which is static random access memory, or SRAM, directly integrated with CPU. It stores the data most likely to be used by the CPU. Cache acts as a buffer between CPU and main memory. There are three levels of cache. Each level is incrementally bigger size, but slower speed. Then the next level below is the main memory. The main memory is the physical hardware where programs and data are all kept when the CPU is using them. The main memory includes physical RAM, DRAM, and virtual memory. The physical RAM is typically around 4 to 16 gigabytes and can be upgraded, but it is still limited in some cases. In order to keep your programs working, your computer starts to expand the memory by allocating some space from your hard disk. This process is called virtual memory. The purpose is to give programmers a perception of unlimited memory, but it'll actually make the active programs much slower. At the bottom of the memory pyramid, it is the secondary memory. This is where the programs and data are stored permanently. This type of memory is thousands of times slower than the main memory, but the size can be hundreds of times bigger. While temporal and spatial locality ensures that nearly all references can be found in cache, or we call it a hit, there are still cases where the item cannot be found, of course. This is called a miss. In this case, the system will try to fetch the item from the lower level in hierarchy. Instead of just fetching this item, it also fetches other items contained within the same block because of spatial locality. Then the fetched block will be placed into the current level of memory. This is called the placement problem. Eventually, the old blocks from the cache need to be kicked out to make a room for new blocks. This is the replacement problem. We'll talk about them next. So this diagram shows the placement problem between two adjacent levels of memory in hierarchy. We will use the main memory and cache as examples. We just learned that the main memory is much larger than the cache. So apparently there is not a one-to-one mapping for each block between them. Fortunately, we only need to fetch a subset of blocks from the main memory. The most straightforward way to map a block from main memory to any location in the cache. This is called fully associative cache. Ideally, this cache will maintain a queue to track the possibilities of blocks needed in the future. If necessary, the block which is at least likely needed will be kicked out to make room for a new block. There are many ways to manage this queue. For example, the Bellides algorithm, FIFO, FILO, LRU, etc. Please note those are expensive to implement in hardware, especially when the queue is very long. To improve performance, we need to have a better way to know where exactly the block goes to the cache. This way is called the direct mapped cache, which maps to a single location in cache. Let's assume each block in main memory has a block index or address. In this case, it is from 0 to 31, 5-bit address. And each location in cache also has a block index from 0 to 7, 3-bit address. So if we only look at the lower 3-bit address from the main memory, each block will be mapped to a single location in cache. This mapping can also be calculated using the modulus operator. For example, the block index of 14 in the main memory, mod, by the locations of cache, which is 8, is equivalent of truncating the last 3 bits, so it will be mapped to the number 6 location in cache. You may be thinking, what will happen to the first 2 bits in the main memory address? In this case, it is 01. Actually, it is also saved in cache and has a specific name called tag. With tag, CPU can always figure out the exact address in main memory. The replacement policy for direct mapped cache is simple. It just replaces the old block with the new one. But here we have a conflict. There are 4 blocks from main memory will be mapped to the exact same location in cache. For example, if CPU is trying to read from 614, 614, 614, each load will kick out the previous block from cache, so each access is a miss, even if the cache has a lot of empty locations. Apparently, we need some hybrid design between the two extremes. This hybrid design is called set associative cache. Basically, it divides the cache locations into sets. For example, if we define 4 sets, each set will contain 2 locations. Now the mapping happens in 2 steps. First, the block address from the main memory will be mapped to a set address in cache. In this case, we have 4 sets. So it is 14 mod 4, which is equal to 2. Then inside the set, which contains the location 4 and 5, the exact location is determined by replacement policies. Just like the fully associative cache, and less chance of conflict than direct mapped cache. We can define the set size as 1, 2, 4, and 8. As you can see, if we define only one set, which includes all locations in cache, then we got the fully associative cache. If we define 8 sets in cache, each set only contains one location. Then this becomes the direct mapped cache. So far, we talked about read. Then how about write? We know the data has multiple copies across the memory hierarchy. Ideally, all copies should have the same value. But what if the CPU updates the data? We'll start with a write hit, where the data is already in cache. When CPU updates the data in cache, this data will have different value than its copy in main memory. One strategy is to update the value immediately, all the way down to the main memory. The strategy is called write through, but as you can see, this will be very slow because it has to go all the way down to the memory, update the main memory. This seems to defeat the purpose of memory hierarchy design. It is useful for the occasional data update. If the data is expected to be reused for a while, then the update to main memory should wait until absolutely necessary. Now comes the second strategy, write back. In write back strategy, we use an extra flag to indicate whether the data has been updated by the CPU or not. This flag is called the dirty bit. Because of locality, the CPU is likely to use this data again and doesn't have to worry about the data on main memory for a while. This will improve performance. This modified data will stay there until it's kicked out at a later time. At that time, if the dirty bit says this has a new value, then it will write to the main memory. Otherwise, the new value will get lost. What if this data is not in cache? That is a write miss. In this case, the data from the main memory will be loaded to cache first. This strategy is called write allocate. Once the data is in cache, the CPU writes to it. Another strategy in a write miss is to simply write to the main memory immediately. This happens if we know we don't need to reuse that data for a while. The strategy is called no write allocate. So far, we talked about 4 strategies for writing, including 2 for hit and 2 for miss. In practice, they typically work in groups. If you want high performance for locality, use write back and write allocate. Otherwise, for occasional data update, you can choose write through and write allocate. Okay, now we have covered the most fundamental concepts of cache design and the strategies for read and write. There are still many other details I don't have time to cover here, but hopefully with what we have learned today, let's try to write better code. In this example, we want to sum up a m by n matrix. We know that in row major layout, as in C++, the first row of matrix is placed in contiguous memory. Then the second row and so on. So spatial locality follows each row instead of each column. So the first row will get put into memory first and then so on. On the left side, the code loops through row by row. For each row tracked by index I, it sums up all the elements using index j, so the CPU loads and accesses contiguous data in stride 1 pattern. That's exactly what cache is designed for. Now, if we actually swap the two loops, then it'll give us something different. It sums up each column first before moving on to the next one. As a result, the access has to jump back and forth in memory, like this. Therefore, the performance is compromised. Have fun and happy coding. Bye-bye.